Um, welcome everybody. This is the Introduction to Parallel R. I'm Rob Bjornsson. I work at the Yale Center for Research Computing, where we do a lot of different things, and I'll talk about that in a second. The materials for the course today are shown here. I don't recommend that you try to follow along during this, and the main reason for that, with your own version of the code, reason for that is there's a fair bit of installation that can be a little bit tricky the first time. So I think it'll be easier if you just watch me and then use these instructions, the Git repository and the install instructions I'll tell you later for after the presentation. But of course it's up to you. What I'm going to show you today is a little bit unusual as an R environment, and so I don't want you to feel confused by that. This is actually a Jupyter notebook, which for those of you who are familiar with Jupyter, you've probably been more familiar with it in a Python context. But you can run a lot of different, what are called kernels, different execution environments in a Jupyter notebook. And I'm running actually an R kernel here. So up at the top of the screen right here, you can see it says R. And the reason I'm doing that is for presentation purposes, it's nice to mix the text of the presentation together with code that actually runs. But when you're actually doing parallel R, it's more likely that you'll run R in a standard, typical way, either interactively on the R command line or in a batch job. And I'll show you a little bit of that later. But most of what I'm going to be showing you here today is inside of this Jupyter notebook, just because that's a nice presentation style. So most of what I'm showing you is within a single Python notebook, Jupyter notebook, which you'll see in this GitHub. Or if you go to this tiny URL, it'll show you a static version, a version that you can't actually execute. You can't execute the R code, but you can look at everything. So hopefully that's clear. I'm just going to spend a minute or two telling you who we are at the Yale Center for Research Computing, in case you don't know. So the YCRC is about 5 years old now. We are an independent center that is under the provost's office, so we're in the academic side of the house. We're not a huge group, we're roughly 20 people, and we exist really to help people with research computing, and in particular to help them do high performance computing and high performance storage. That's kind of our specialty. And as such, we manage all the high performance compute clusters. We help users use those clusters. We do consultation and education like this, and so forth. Normally, we're located at 160 St. Ronan. If the world were normal, that's where we'd be right now in our conference room there. But today we're not. We have a website, which I think you're probably all familiar with because you used it to sign up, but I'll just show it here. And we have a help system that you can access via this email address. If you have questions, I think what we're going to try to do, if I understand this correctly, is you can enter them in the chat, and Christine, my colleague who's monitoring this, will let me know that there are questions, and we'll try to handle them. Okay, so let me just sort of give you an overview of what it is that we want to cover today. I'm going to start with a short but I think important level setting introduction to what parallel R is. Then I'm going to spend most of the presentation on one particular way of writing parallel programs in R. It's called for each. One of the difficulties with parallel R is there's a lot of different ways to do it. and it can be very confusing. And I found that for each is a relatively straightforward way of doing most of the things that you'd want to do in Parallel R. So that's why I'm focusing on that. I'll introduce you to the basic concepts of for each, and then go into some examples of actually doing it. And then finally, I'm going to show you some options other than for each that can be very useful in specific settings. Okay, so what do I mean by Parallel R, just to get started? Well, as I mentioned, there are a lot of different ways to write R programs that are parallel. By parallel, I mean they're going to use multiple CPUs in order to compute faster, essentially. And that's really what the game the game is in high-performance computing. That the individual computers in high-performance computing really aren't that much faster than normal computers, but we have a very large number of them. And so typically these days, when you want to speed up a code by running it in parallel, you're going to use a large number of CPUs and spread your computation out across those CPUs and hopefully have it run faster. So the simplest way to do that, and a very profitable way, because it's so easy, is to simply run a lot of sequential, absolutely sequential normal R jobs at the same time. And at the end of this presentation, I'm going to show you a very simple way to do that. So that's perhaps the easiest way to do it, because it just involves running a lot of copies of something that you're already used to running. There can be a little bit of complexity in managing lots of different jobs and combining the results, but fundamentally, the code itself is pretty straightforward. But what I'm going to focus on today is the more typical or more traditional meaning of Parallel R, which is a single program that's computing some computation, and you want to speed that single computation up. And by far the simplest case of such a program is one that has a loop, or perhaps several loops, where the individual iterations in that loop are completely independent from one another. So they could be done in any order. They can be done at the same time. So that's kind of the simplest nice case, where you've got this loop and it's where you're spending most of the time in your computation, but each iteration of the loop is independent of all the others. It doesn't depend on any of the others. And that is a pretty common case, pretty common circumstance. And if you're fortunate enough to have a program that's set up like that, that has one of these loops that's has independent iterations, then for each is going to be perfect for that. And that's really the case that we're going to talk about. Now, of course, the world is never quite that easy, and there are R programs, or programs in general, where the individual elements of the program depend on one another, and where you can't just simply take a loop and deconstruct it. And so that's a case where parallelism is going to be much more difficult. It's really an advanced topic, and I'm really not going to cover that today, because this really is an intro presentation. So we're going to focus pretty much entirely on case 2 here, where we've got some kind of loop of independent iterations, and we want to find a way to do that thing with lots of different CPUs so that the computation happens faster. So it turns out that the first serious hurdle in running Parallel R is to get yourself a version of Parallel R installed. And I struggled with, when I was putting this course together, I struggled with this more than I expected to. And I think one of the values of this presentation, perhaps one of the main values of this presentation, is that with a lot of effort, I found what I think is a straightforward and nearly foolproof way of installing Parallel R so that you guys can have a way to do that without going crazy. And the way I did that was by using the Conda environment. And if you're not familiar with Conda, you should be. It's an incredibly powerful software management and installation environment. It's again something that you normally see in the Python environment, and sorry, in the Python world. It's normally a way of installing Python, but it turns out that it's also been used for lots of other things, including R. And so essentially what you want to do is to install Conda. In this case, I used a version of Conda called Mini Conda, which is a stripped down version of Conda. And on the clusters, the way we do that is we say module load Mini Conda. If you're not running on the clusters, you can just follow the instructions that you would find on the Conda site for how to install either Mini Conda or Conda. On the clusters, we install that part for you, and you just use it by saying module load Mini Conda. So having done that, then you can create a new Conda environment like this. So this sort of long invocation, what it's doing is creating a new environment called Parallel R. You can name it anything you want. And it's installing these 4 important packages, which are all R packages that are involved with either R directly or with the parallel stuff we're going to do. So R based. Yep.
In the chat, what about the future package? Is it good?
I'm not familiar with that. I'm sorry. I don't know what that is. R base and R essentials are basically just installing R. And these two, doMC and RMPI, are, as you'll see, what we're going to use for doing the parallel R stuff. Conda Forge, this is something called a channel, and it's just a software repository for Conda. So these R packages all happen to be hosted in the Conda Forge channel. Doesn't necessarily need to understand this deeply, but this is just a way to create yourself your own R installation with all the parallel stuff installed in such a way that it's easy for you to add on other packages as you need to. There's one final little bit here that's perhaps unfortunate. For some reason, the doMPI package, at least the last time I checked, was not available in Conda Forge. And so that last bit you have to install in this normal R-ish way. So you start up R and you do an install packages. That hopefully somebody will fix that. You should be able to install R doMPI the same way that we did R doMC here. Okay, that was really just for reference for in the future when you want to install your own parallel R environment. You can follow those directions, and if you run into trouble, feel free to reach out to me and I'll try to help. But I wouldn't encourage you to do that now, just to repeat, because it could take you a little bit of time to figure out. Okay, so as I mentioned a minute ago, one of the barriers to doing parallel R is that there are a lot of different packages associated with parallelism in R, and it's really a confusing situation. And the reason for that is as follows. Let's see if I can explain this. So the original, there were 2 original packages for doing parallelism in R. One was called Snow and one was called Multicore. These go back quite a number of years. Snow was used, I believe it stood for Simple Network of Workstations. And Multicore is another package that used forking to do parallelism. So Snow was for taking a bunch of computers and basically treating them like a supercomputer back before there were really clusters. And Multicore was a way to use multiple cores on a single workstation, on a single computer. And those 2 things arose independently and caused a huge amount of confusion because they were similar in ways and different in other ways, and it kind of drove everyone crazy. So then there was this bright idea to create a unification called parallel, which attempted to unify those two. And perhaps it did, but in my opinion, it just created more confusion because now we had 3 packages that all did things that were very similar. So about the time things were getting really confusing with that, a colleague of mine, Steve Weston, created his own interface called For-Each, which, as I've said, I like a lot. And it attempted to do things at a simpler, higher level. And it's actually a layer on top of these other things. So it's using those, but it cleans it all up. And so again, that's what I'm going to focus on. The thing is, if you do Google searches on Parallel R, you're going to find lots of different things referring to Snow, referring to multicore, referring to Parallel, referring to For-Each. And they're all a bit different, but similar enough to be confusing. So I just want to warn you that you're going to see, if you Google, lots of different approaches to this stuff. And it's important to try not to let that confuse you if you're following other people's examples.
Rob, we have another question in the chat. Sure. What about multi-DPLYR for parallel computing from Tidyverse?
I'm not too familiar with that either. I'm really just focusing on For-Each in this presentation. There are so many of these things. It's as I said, there's been a proliferation of different approaches, and if you find one that isn't For-Each and you're happy with it, that's great. My intent here with this presentation was to show a very basic, simple approach that I think is approachable for beginners, to be honest. Okay, and in that spirit, you may run into references to RMPI, and I would really encourage you not to do anything with that as a beginner, except that it'll turn out we're going to use RMPI underneath For-Each when we want to parallelize across multiple machines. But that's a very simple usage, and you're not actually using the RMPI API directly. Okay, I'll mention that Steve wrote a very nice slim book called Parallel R by the O'Reilly Press, which does a very good job of explaining Snow, multicore, and parallel, and also RMPI, if I recall. It does not touch on For-Each, unfortunately, because it was written before he wrote For-Each. So for For-Each, you are really dependent on online documentation, which I'll show you below. Okay, so these 3 approaches are all fairly similar, Snow, multicore, and parallel, in that they all have the idea of parallelizing an apply. So those of you who are confident R programmers know that R loves to do applies instead of for loops. And the idea behind these 3 are all that you're going to do that apply in parallel. For-Each, is different in that it actually does an explicit for loop. So that said, the idea behind all 4 of these approaches, Snow, multicore, parallel, and For-Each, is that we're going to apply a function or some code to a large number of inputs and get the same number of outputs, essentially. So it all kind of feels like a parallel apply. It's just the syntax is a little bit different. Okay, so why do I like For-Each? I think it's easier to use. I think it's more general than the parallel apply approach that Snow, parallel, and multicore used. It's got very natural semantics. It just feels like a for loop. Here are a couple of links to the formal documentation and a very nice vignette that Steve wrote. So you can have a look at that when you have time. The nice thing is that it works on the two important contexts in which you want to run parallel programs, either a single machine with a lot of CPUs or on many machines that are connected with some sort of network and also have many CPUs, each one of them. So it can span both one machine with lots of CPUs, which is what the original multi-core did, and many CPUs across many machines, which is what Snow did. So it's kind of one approach that works everywhere, without, as you'll see, without having to make significant changes to the code. The thing I really like about it is it does a good job of managing the environment that the parallel workers see. And we'll talk about that a little bit later, but that's really a key thing. So in its absolute simplest form, the way for each works is it looks like a for loop. And we're going to iterate over some arguments, some parameters, and we're going to execute an expression for each set of those arguments. So this expression, it's going to be some R code. We're going to execute that multiple times, one for each set of arguments that we get out of here. And we're going to, by default, return a list of each of those results back. So here I've set it to L. So if you're familiar with a parallel apply, this does feel a lot like a parallel apply, just with slightly different syntax. Now behind the scenes, you can see here there's nothing here that really says anything about how we're going to run this thing in parallel. How is it going to be spread out across multiple CPUs or perhaps even multiple machines? And that's powerful in that those details have been abstracted away from the for each. And the way that works is for each requires a backend. So before you run a for each, you need to have created and registered a backend, a parallel backend. And that's the thing that actually is going to be responsible for managing all the spreading out of the work and gathering the results. So there are a variety of backends. And as you can see here, these backends actually look a lot like those traditional parallel R methods that I mentioned briefly before. So there's a do MC, which is basically using multi-core. There's a do Snow, which is using Snow, do parallel, and do MPI. Of these, do MC is by far the simplest to use. It's very straightforward, very easy to install, very simple to use. So that's what we're going to use for the beginning here. We'll move on to do MPI, which is how I recommend you run parallel programs across multiple machines. We'll look at that a bit later. So for now, we'll focus on do MC. And again, you can think of do MC as a thin layer between for each and the pre-existing multi-core package in parallel R. Okay. So this is what that looks like. So this is kind of the setup. Now I'm actually going to start running real code. I should explain again my context here a little bit. So this is a Jupyter notebook running an R kernel. I'm actually running it on the Grace HPC cluster that we run. And I've created myself an allocation there that has 8 CPUs. So I'm actually running this Jupyter notebook inside of an allocation with 8 CPUs. So if I go ahead and execute this bit of code here, all I've done is loaded these 2 libraries. And then this is registering my backend, my multi-core, my MC backend. And it's telling the backend that I want 8 workers when it actually runs a for each. That's what the 8 means. So normally what I'm going to do is pick the same number here that I've picked when I did my allocation. Or if I'm running just on some computer, I'll know how many CPUs my computer has. If I have a laptop with 4 CPUs on it, then I would put 4 here. So this is just saying sort of what is the scale of my parallelism. Okay, so let's actually run a for each here. I'm just going to run it and then I'll explain it. So ran pretty much immediately, and you can see what we got here was the square of all the numbers between 1 and 30. Let me just make this a little easier to see by making a smaller number. Okay, so let's pick this apart. Some of this is very straightforward R, and some of it probably looks a little mysterious. So this is very simple. This is just the sequence of numbers between 1 and 5, as you've seen in R many times. So what this is doing is saying, I want my variable R to take on, my variable I to take on all the values between 1 and 5. Now, for each, the syntax here is you say for each, and your iteration variables, this custom operator, do par. This is just syntax, don't worry about it too much, but this is the way you do a for each. You say for each, some iteration variables, do par, and then the code. So this is a code block, all of this here, and that is what is going to be executed once for each of my iterations. I have 5 iterations. I is going to be set for all the values between 1 and 5, and each of those iterations I'm going to execute this code here, and so you can see exactly how that works. And then I just print out the value below, because what we've done here is to assign the list, which is the return from for each, to res. Okay, so that's all there is to that. And you couldn't really tell, this is such a simple computation, but this execution was actually farmed out to 5 different workers that are running on my allocation on Grace. So these 5 values were actually computed in parallel. Now, to make that a little bit easier to see as we move along, I'm going to create a little function here that basically simulates computation by spinning for a certain amount of time. So I'll just go ahead and define that function. You don't really need to look at the contents here. You can look later if you're curious, but the important point is if I run spin and some number, it's going to take that many seconds for it to complete. And then it's actually going to print out how many seconds it spun. So I can do a different number here, and it'll spin for that amount of time. So it's just a utility function that I can use as we experiment a bit with for each. Okay, so now let me show you, I'm going to actually put a function call inside of my for each. So here I'm doing for each on the numbers 1 through 8 and invoking the function f on that number. And what the function is going to do is spin for 5 seconds and return the square. So I go ahead and run that. This will take a few seconds to complete. And I also, if you see here, I wrapped this invocation with the utility system time, sort of a handy R utility that will tell me how long the execution took in terms of elapsed time and also user time. So looking at that, we can see that the total execution took about 5 seconds. So that's proving that this was done in parallel, because we did 8 executions, each of which took 5 seconds, and our overall time elapsed was 5 seconds. So it looks like it was done nicely in parallel. There was total user time of 34, almost 35 seconds. And I have to be honest with you, I'm not sure why this isn't 40 seconds. There's something strange going on here with system time, because I would have expected to see 8 times 5. And I saw this yesterday, and I haven't been able to figure out why it's not showing 40, but it's not. But we can see that we're getting, as our return value, all the different f of i's and printing them out here. Don't be too confused. This output that we're seeing here with these 1.1, 2.4, etc., that's just the R kernel's way in Jupyter printing out a list. It's kind of strange. If you were running this in a native R environment, you would see your normal list output here. But for whatever reason, this is the way that Jupyter R kernel prints out a list. Okay. One interesting thing you can do is, instead of saying do par, for testing purposes, you can replace it with do, and then the execution will be done done sequentially rather than in parallel. So it won't start a bunch of workers and run on a bunch of CPUs. So if I go ahead and do that, I'm doing 2 iterations now of 5 spinning by 5, and it should take about 10 seconds to complete, and it does. So obviously this isn't terribly useful for running in production, but for debugging code, it can be very useful. Now, we don't have to put a function in the block. We can put any arbitrary code we want, and the value for the final value for each iteration of the for loop will just be the final statement in the block. So this is equivalent to what I did before. I should mention that when I do this execution, this turns into an asterisk showing that the kernel is busy. And then once the kernel finishes the execution, it turns into this integer. So we get the same value. Okay, so let me pause there just for a second and see if there are any questions about the original, this initial stuff having to do with for each. Okay, doesn't look like I see any. Let me move on to combiners. So as I mentioned, by default, a for each returns a list of all the values of each of the iterations. But there are many cases where it would be more convenient if you combined those values into something else. The word that Steve chose for this was combine. I actually sort of think of it as a reduce operation, if you've heard of reduction. The basic idea is, as values come back to the for each, it's going to take pairs of those values and combine them together into some unified value. So a very simple example of that would be a plus combiner, an addition combiner. So the idea there is, instead of getting back a list of integers, we're going to get back a single integer, which is the sum of all of the component integers. So if I go ahead and run this thing, we get a single value back 204, which is the sum of all the squares of the numbers from 1 through 8. And I can prove that by running this little bit of R code here. So combiners, the idea behind combiners is you can essentially use any function that will take 2 values and return 1 value from them. And then the combiner will be iteratively applied to all the values that come back and essentially reduce everything to that collection of values to a single value. So here we used plus. There's some really obvious ones that should make sense to you from R. In addition to plus, there's multiply as an asterisk. There's C making a vector. So basically you're going to get a vector instead of a list. Really handy, and we'll see this later on in a sort of a realistic example. C bind or R bind can be used to form matrices and so forth. You can also use essentially any arbitrary user supplied function that takes two variables, 2 arguments. So for example here, I've created my own max function, which just returns the max of the input values. And I could use that as my combiner here. So now I'm going to get the maximum value back from the for each. So our biggest value was 8 squared. Now, one little gotcha here, and I know about this because I stepped in it myself and had to figure out what was wrong. If you forget to put the dot here, so I should actually back up. I haven't shown you the full definition of for each, and I probably won't show you everything, but there's a set of values you can put here of parameters that are all beginning with dots. These are sort of useful secondary parameters that can steer the way for each works, and one of them is combine, so dot combine. If you leave that dot off, strange things will happen. So let's actually run this and see what happens. So I was expecting to get 10 iterations done and then sum together those values, but instead I got just the number 1 back. So what happened was for each saw combine as just another iteration variable. So it thought that it was supposed to be iterating over 2 different variables, I and combine. And if it is given 2 sets of variables and they're not of equal length, this one is 10 in length and this one is only 1 in length, it'll do the shortest one. And so the effect of this code here was to do a single iteration with I set to 1 and combine set to plus. So all we did was spin for 1 second, return 1 times 1, and ignore combine. It was never used down here, so it had no effect. And that's why we just got a 1 here. So you just want to be really careful that you don't miss that dot there. It can be very hard to see if you miss it. So that introduces the idea of multiple indices. So everything I've shown you so far, we're only looping over a single variable, but you can loop over multiple variables at the same time. So here's an example of that. Here I'm going to iterate over I and j. I is going to go from 1 to 3, and j is going to go from 10 to 12. Now, you could think of 2 different ways of looking at this, or this could have been defined 2 different ways. It could be that we're going to take all the combinations of I and j, or it could be that we're going to take 1 of I and 1 of j, do the next of I and the next of j, and so forth. And that is actually how it works. So this specification here is going to give us a total of 3 iterations. The first one has I equal 1 and j equal 10. The second one has I 2 and j 11, and so forth. So if I go ahead and execute this code, you can see that we get the value 1 times 10, 2 times 11, and 3 times 12 as our outputs. So that's how that works. Now, as I briefly mentioned with that combine bug that I ran into myself, you want to be careful that your iterations have the same length. Your different variables have the same number of elements in them. Because if they don't, you're going to only iterate over the shortest sequence. And so in this case, the I equals 4 iteration will never happen, because j only has 3 elements and I has 4 elements. Any questions about that so far, about how this works? Okay. So I think I'm going to just back up for a second here and go back to one of my larger executions here. And I want to show you, I want to prove to you that this is actually running in parallel. So believe that I have So for those of you who are familiar with our HPC clusters, what I'm doing here is I'm on the Grace cluster, and I'm going to find my allocation. So this is the allocation that I've actually been running all of my Jupyter Notebook executions in. You can see it has 8 CPUs, and it's on this particular compute node. So I'm going to go over there in this shell window. And run top. So this is showing all of the processes that I have running on this compute node. And you can see that I have, it's a little hard to see actually that way. You can see I have my notebook and my R kernel. So let me go ahead and rerun this execution here. Quickly go back, and we can see that I've got a bunch of R processes. These are the workers. Now that went a little bit too fast. Let me do it one more time. It's a little bit longer of an execution. I will spin for more seconds. So you can see that pretty quickly these R jobs run up to 100%. And so I've got basically 8 processes that were briefly running there at 100%. And so why do I show you this? I think it's really important when you're running parallel executions that you check that your code is actually running in parallel, that you're actually using all of the CPUs that you allocated, and that your code is doing something with each one of them. And a very simple way to do that on the cluster is to run top on the compute node where your allocation is. We run into a lot of cases where people allocate a lot of CPUs and start a program that they think is parallel, but for whatever reason isn't, and they waste n-1 of their CPUs. So it's a good idea to double check and make sure that things are working as you expect. Okay, so I just showed you how to iterate over multiple variables sort of in sequence like that. You can also nest for eaches, and the syntax for that is a little surprising. This is what it looks like. You use this colon operator, %, %, to separate the 4 eaches. So this is an outer for each that loops over 1 to 3, with an inner for each that loops over 1 to 4. Then you have the do par, and then the actual code block that's going to be executed. So this is going to be a total of 12 tasks. Each of those 12 tasks will be run by one of the workers, one of my 8 workers. And the result, if a single for each gives you a list, it, I suppose, makes sense that what we're going to get here is a list of lists. So the outer for each will make a list out of the lists returned by the inner for each, and so that's why we end up with a list of lists. I didn't put a spin in here, so the execution was very fast, but we can see that the output is what we expect. Now, again here, Jupyter is doing me the dubious favor of this kind of outline format, which I don't really like. That's what this 1A is, 2 and A. Our actual values are these values here in the column. 1, 2, 3, 4, which is 1 times 1 through 4, and then 2, 4, 6, 8, which is the 2 here for the I and all the J's and so forth. So we get this list of lists. We can do the normal list dereferencing like this. We can ask what the types of things are. So that's basically how that works. And you can nest for eaches deep in this. You could have 3 nested for eaches and so forth. So here's an example of using cbind as the combiner to turn what was a list of lists into a matrix. So this I think is genuinely useful and kind of interesting. So we're going to do exactly the same computation we did before, except that for the inner for each, we're going to turn the list into a vector by doing this, by using the C function to combine our elements into essentially to convert our list into a vector. And then on the outer for each, we're going to use cbind to glue those vectors into a matrix by column. So this is very R-ish kind of stuff, but it works really well. And you can see that what we end up with is a matrix. And again, here, this is sort of the strange output for the Jupyter Notebook, but the elements of the matrix are correct. Okay, so that was a quick run through of the very basic elements of using for each, and then a few more advanced topics like multiple indices and nested loopings, and a little bit on combining. So before I move on, any questions about any of that? Okay. I wanted to say a couple things about running this stuff on Windows. So again, everything I'm showing you right now is in a Linux environment, actually on one of our HPC clusters. What I've done, and if you're on a Mac, everything would look very similar. Windows is a little bit different. So I just thought if you want to run this stuff, this for each on a Windows computer that has multiple CPUs, you can, that's fine. Just a couple of things to mention. One is that doMC is, which is the backend that we've been using so far for each. It, under the covers, is using multicore, and multicore is fundamentally fork-based, Unix fork-based. Fork is a really powerful tool, and it's one of the things that's making things so easy for us. But unfortunately, fork is not something that Windows supports. So if you're going to run for each on Windows, you don't use doMC. Instead, you use do parallel. So a little bit of the code changes. You need to do these three things here rather than what I've been doing so far. So just to remind you, what I've been doing so far is was very simple. Just basically library doMC and register doMC 8. It's very simple with MC. With Windows, you can also do this on Linux. It's really the issue of using do parallel. When you use do parallel, you need to do a two-step process here. You need to make a cluster and specify the number of CPUs, and then register that cluster. But otherwise, your for each will look exactly the same. And then in terms of installing all this R stuff on Windows, you can also do it in Conda, which is great. So it's basically the same installation process. The only difference is you're going to need to install rdo parallel, because that's the backend that we're going to use. But otherwise, should basically work the same. Okay. As I said, I've been doing everything inside this Jupyter Notebook, but that's really not the way you're likely to want to do this in production. And so I want to say just a few things about how to do this in the context of running on the HPC cluster using Slurm, which is Slurm is the management system that we use on the cluster for managing jobs and resources. It's actually very simple. Just a couple of things to keep in mind. So first, in order to run in parallel on the cluster, you're going to need to get multiple CPUs, multiple cores. If your allocation is only one CPU, then no amount of parallelism in the code is going to give you improved performance because you're going to be trapped on that one CPU. So the first thing to make sure you do is use the Slurm flags to ask for multiple CPUs. That's -C or CPUs per task. Those of you who've run anything on the clusters, you're probably familiar with what I'm talking about. And then the other thing you want to do is make sure that you do a register doMC specifying the number of cores that you asked from Slurm. Now you can either do that manually, which is essentially what I've been doing, right? I've just been saying register doMC 8. That's not terribly flexible, and a cleverer way to do it is to realize that Slurm sets an environment, keep doing that. Slurm sets an environment variable, Slurm CPUs per task, that you can then query in R to figure out how many cores you're running inside of, and just use that value. So this is a little bit of crufty R code that will see if there's an environment variable set to tell you how many CPUs you have. If there isn't, default to 1. Set that value to cores, and then use that in your register doMC. So this is just some boilerplate code for letting your code automatically figure out how many CPUs it has access to and register that number. Okay. So in a little more detail, a batch script, a Slurm batch script that would run a parallel R job might look something like this. So we'll tell Slurm that we want 4 CPUs. We'll load Miniconda. We'll activate our parallel R Conda environment, and then go ahead and run our R script. And this is a sort of standard way in R to run a script on the command line. So let me actually show you that for real. Again, I'll go to my this is just my login on Grace, my SSH login. So I have the GitHub repo, not there, here. And in here, if you were to put, this is just the GitHub repo that I mentioned at the beginning of the presentation. So you can pull this stuff down too. Just to mention, this is actually the presentation I'm working in, so, the Python notebook. But I want to show you the examples, which are down here. And the first one I want to show you, sorry. So this is a very simple R code. This is very similar to what we've been doing in the Jupyter Notebook all along. We're just going to basically do a for each here. From 1 to n starts, and invoke some function inside there. Here's the function definition, which uses spin, and I abstracted spin out into another file here, so it's being sourced. N starts is set here, so our loop here is going to be from 1 to 20, and then just the standard library initialization up here. So this is logically very similar to what I've been showing you in the Jupyter Notebook so far, with possibly this exception that, as I said, this code is, rather than hard coding 8 in here, which is what I'd done before, we're going to be reactive here and just figure out however many CPUs we were allocated and use that number. So this is the R code we're going to run. And let's look at the batch, the sort of matching batch script. So this is what I just showed you. Basically, we're going to ask for 4 CPUs and load Miniconda, activate our environment, and run the code. So let me go ahead and do that. I'm going to cheat a little and use a an internal partition that you don't have access to, but that will make sure we don't have to wait. And if I look, here is my job running. I'm going to quickly, I hope, go there, C34N03. And it's just in time. Okay, so we can see my 4 jobs running there. Only 4 this time because my batch script asked for 4 CPUs, and my R script noticed that the number was 4 and registered 4 as the number of workers, and so we can see it running here. I think that'll take about a minute to run, and no reason to watch it to the end. Okay, so that's the basic way that you would take the kind of code that I've been showing you and convert it into a batch script that you could run on the cluster. So if you look in there, you know, that boilerplate will get you started on doing that with your own code. Does anybody have any questions about how to run parallel R code as a simple batch script like that? Or did that make sense? Okay, I don't see any questions. I want to take a moment to mention something called the iterators library, which works really nicely with for each. It's a separate project, but a very powerful project. Basically inspired from Python. Python has a very rich set of functionality called iterators, where iterators are things you can just repeatedly query them, and they will return you something each time until they run out of things to return to you, at which time you stop querying them, essentially. So it's a way of flexibly looping by querying an object for values. And the same idea works here. And it just turns out, since for each is iterating over things, it's a natural pairing. iCount simply iterates that many times without setting any variable. So it's kind of a nice, concise way of saying, I want you to do something that many times. So here what we're going to do is we're going to do a for each that, that runs 1,000 times. Each time it returns a 1. It's kind of a silly example, but when we combine it, we should get 1,000 ones added together. In other words, we'll get 1,000. Iter is an iterator that can take an arbitrary function and turn it into an iterator that can be used. So here what I've done is wrapped this function with this iterator, so that now ifun is its own iterator, and I can just query it over and over again. Now, in this case, you can see that the function is never going to run out of values, so this is an infinite iterator, which is kind of one of the cool ideas about iterators. You can create iterators that never end. Here, what we're going to do is kind of combine those two ideas. So this is an iterator that returns a bunch of random numbers and assigns v. And then the other iterator that we're going over is this, I call it an anonymous iterator that's just going to iterate 10 times. And if you recall, one of the features of multiple parameters in a for each is you only iterate the length of the shorter of the set of iterations. So here I'm going to, even though this one is infinite, this one has 10 values, and so I'll iterate 10 times, and each time v will get set to the value returned by this iterator. If I do that, I'm going to get 10 sets of 4 random numbers. So, you know, what this is doing is sampling the numbers between 0 and 9, giving me 4 each time with replacement. And so that's exactly what we see here. So kind of a cool use of iterators and for each. You notice I'm using do here just because I don't want to bother to do this in parallel for the example, but it wouldn't change the values. Okay. And of course, I can do more complicated things. So here I actually catch the value of I count and assign it to I. And so I can return a vector of the I and the V's as I go. Okay. Any questions about iterators? Okay. So I want to now move on to how to...
Rob, we do have a question.
Yep. Oh, sorry, didn't see it.
What if one worker throws an error? Does the entire for each give an error?
Yes, you're going to get an error for the for each. Yep. Yeah, we should. I should have an example in here to do that. It's an excellent question. Okay. So. So far, what we've been using is doMC as the backend. And doMC has a couple of very important advantages. It's very simple to use, as you can see. It takes essentially no setup at all. The other thing that isn't obvious but is really powerful, almost I think we took it for granted, is that because doMC is based on the Unix fork function call, system call, you automatically inherit the environment of the parent. This is a little bit complicated, but it's very important and powerful. So let's just go back up here to an example of a for each. It's not a very interesting one. So yeah. I think I'll show you this later with a better example. But the important thing here is that at the point that the for each begins, when those workers are spawned, they get everything that the parent code has at that moment. So in particular, you get all of the variables that were assigned at that moment, and you get all the libraries that have been loaded at that point. So the workers, you don't have to explicitly tell them to load all that stuff. And this is really one of the key advantages of for each over some of the other approaches, is that environments are handled really well. And for doMC, it's actually handled by doMC automatically, because doMC is fork-based, and fork gives all the children the full environment. So that's really powerful. The problem, of course, is that it only allows you to get as big as a single machine. Now, modern machines can have a lot of CPUs. Some of the cluster machines, the nodes on the clusters that we have now, have as many as 36 CPUs. So you could run in parallel up to 36-way parallelism, which is pretty good. But if you wanted to go to hundreds or thousands of CPUs, you're going to need to use multiple computers, multiple compute nodes in the case of the cluster. And so doMC isn't going to help you with that. doMC is fundamentally limited to the resources of a single machine. So we need a different backend. And as I mentioned near the beginning, there are a number of different backends, including doSNOW, doParallel, doMPI. It's my advice that if you're running on the cluster, if you're running one of our HPC clusters, and you want to run on multiple nodes, that you use the doMPI backend. That integrates, the reason I suggest that you do that is it integrates with Slurm really nicely. Things start up and stop nicely. and it works really well. The major problem with that always was getting the installation right, because MPI itself is a very complicated install. So like combining the R plus the parallel R plus the MPI could be a challenge. But the steps that I showed you at the beginning, I have found work perfectly to get you a complete set of stuff you need in order to run the do MPI backend. And that's why I think it's a good set of instructions. The beauty though, and I mentioned this before, is when you change the backend, almost nothing has to change in your code. So to run your parallel code across multiple nodes on the cluster using do MPI requires extremely minimal changes to your code. And here's what they look like. So before, what we did was this. Before, we loaded the doMC library, and then we registered some number of cores. To switch that to use do MPI, we need to do this stuff. So we load the do MPI library, then we create a cluster, an MPI cluster. These are not necessary. These are options that help in debugging. So I recommend that you do them. It'll basically cause some log files to be created in a subdirectory called log, and it'll tell you as it's starting and stopping things, but this stuff is optional. And then you register that cluster. Now you notice here, nowhere in start MPI cluster did I say how many workers I wanted. And you can specify that, but I recommend that you don't. It turns out that MPI and Slurm will communicate very effectively with one another, and this start MPI cluster will learn from Slurm how many tasks your Slurm allocation has, and it will start the right number of workers. So if you do it this way, you don't have to worry about making being consistent between your MPI cluster and your Slurm allocation. It'll just work automatically. Finally, at the end of your program, you have to do this stuff to clean up. And it's important that you don't forget to do that, or your program, I have found the program will hang if you don't do these final steps. So just to recapitulate here, in the simple case for doMC, we were doing this, and all we need to do is replace that stuff with this, and the rest of the code can stay the same. And then we could just go ahead and run it on the cluster. This is very similar to what I showed you a minute ago using doMC. This is going to use do MPI, and the only important change here is that instead of asking for multiple CPUs with -C, I'm asking for multiple tasks with little n4, and I'm going to force those tasks across multiple nodes by using a capital N4. For those of you who've been, if there are any of you who've been in my or any of our intro HPC presentations, you may recall that we say never use these flags. But this is the case, this is exactly the case where you do want to use these flags, because you're fundamentally running on MPI here. And MPI is the one case where you want to start multiple tasks with -N. Let me show you that in real life. So that same directory here is ex1 sh, which is the batch script that I just showed you, and ex1 mpi.r. This is pretty similar to what you saw before. So we're just doing this this for each here. This is essentially exactly the same as the previous version, but you can see I've added or made the changes here to use an MPI cluster and clean things up at the end. So I will go ahead and run this one as well on the cluster. quickly see where I'm running. You can see I'm running on 4 different nodes now because I forced it to. I'll go to one of them. So you see you have one instance of R here running at 100%. That's because I forced my 4-worker program to be spread out across 4 nodes. So each of
we
the
can't
nodes got
see
one
your
of them.
screen.
Okay. What? Do you lose the screen?
Yes.
Okay, hang on. Sorry about that. Thank you. Okay. So sorry that you missed all. Let me just repeat that really quickly here. So I'm going to do an S batch of this script. Then I'm going to see where it's running. It's running on these 4 nodes. Then I can SSH to that node and see what's happening. See that I've got one R worker who's using 100%. Okay. So I just want to emphasize sort of how nice this is, that you can first of all get your code running using just %do % and for each. Get it running on a single CPU, make sure everything works without even running in parallel. Then replace the %do with %do par %, and run it on multiple CPUs on a single node in the way we've been doing all along. And then you can greatly expand the parallelism available to you by running it on an MPI, a do MPI backend across multiple nodes, and get tens or hundreds of CPUs all working on the same problem. Okay. So you don't have to use do MPI, and in particular, if you're, for instance, if you're running on a Windows box, you might want to use do parallel. I'm not sure I'd recommend do snow. What do snow works is, the way do snow works is it uses SSH to start workers on multiple nodes. You essentially give it a list of machines, and then do snow, when it creates a cluster, it SSHs to those nodes and runs a worker. I would stick with do MPI on our HPC clusters because, as I said, it integrates much better with Slurm. So it's just going to be much more straightforward. A couple of gotchas I ran into when I was initially working through all of this stuff. It's a little bit surprising. So when you do MC and say do MC 8, as we did initially, you're going to have 8 workers, and if you run a parallel for each, you're going to have 8 jobs running at the same time. With do MPI saves one of the tasks as the master task. So if you ask Slurm for 8 tasks and you run a for each loop, you're actually only going to have 7 workers, because one of your 8 tasks is going to be reserved for the master. And that's one of the reasons I recommend that you don't tell the MPI cluster how many workers you want. This is the way you would do that. This is saying you want 3 workers, but I think it's better to just let Slurm tell the MPI cluster how many tasks are available. Turns out it is n tasks minus 1, which is a little surprising when I saw it. It kind of makes sense. And I will caution you that for whatever reason, you don't want to use the Slurm variable n tasks to figure out what the right value is, because it won't work. So just a warning. Okay, so that's enough for the do MPI for now. I just wanted to show you how easy it was. Any last questions on that do MPI or running across multiple machines? Okay. Now I'm going to take up just a little bit of a tangent here and talk to you a little about random numbers and for each. And random numbers and parallel programs are potentially problematic area, and you need to understand both what it is that you want and what it is that you're getting so that you don't get confused, because you could want different things and you might not be getting what it is that you think you're getting. Generally speaking, each worker in a for each is its own process, and therefore it has its own random numbers stream. So the random numbers are not being coordinated between the different workers. So you need to be careful in two different ways. You want to make sure that, so one of the classic things that you might do in a for each is run n different functions where the functions are exactly the same except they're getting different random numbers. So you're just sort of doing like some kind of Monte Carlo, and you want to execute 1,000 different iterations, and the only thing that separates those 1,000 different iterations is that they're going to choose different random numbers and therefore describe some kind of distribution. Well, you better be careful that they really are getting different random numbers, because if they're all getting exactly the same random number, then you're just performing exactly the same computation 1,000 times, and it's not doing what you think it's doing. So that's the first thing you want to be careful of. And the second thing you want to be careful of is sometimes people want to be able to reproduce their random calculations. So they want to be able to set a seed at the top and then run their calculation such that they know they could go back later, and by setting the same seed, they could reproduce exactly the same results. And so both of those things can be a little bit tricky in parallel programs. So I just wanted to talk about that a little bit. So here's an example of a for each where I'm just going to generate 5 random numbers with my for each. And I'm going to do it sequentially. And I'm going to set the seed to 1 here. So if I do this, every time I run this, I'm going to get the same 5 random numbers. Okay? I've set the seed to some number, and I draw my 5 random numbers. If I set the seed differently, of course, I'm going to get different numbers, right? But I'll get, for a given seed, I'm going to get the same number. So let's look at what happens if I turn that into a parallel run. All I changed here was I made this do pair instead of do. Getting different numbers every time. So what happened? Well, it turns out I set the seed in the master, but the workers did not see a seed get set. And so the workers are just generating R norms without having a seed set. So they're each generating their own random seed, which probably has to do with the system clock and possibly their process ID. And so my setting the seed had no effect. Okay? So what you want to do, if you want reproducibility, is you want to set the seed in the worker. So that's what I'm doing here. Okay? So here I'm going to get the same reproducibility I had before. Now it's important, of course, I wouldn't want to do this, right? I wouldn't want to set it literally to the same seed. That won't do anything. I need each worker to have a different seed, a consistent different seed, okay? Right, so that's basically what I'm saying here is make sure that each worker gets its own distinct, recorded, but different seed, okay? Any questions about random numbers? Just something to be aware of if your code is using randomness, that you want to make sure you understand what it's doing. It can be really helpful to do testing so that you believe that you're getting the kind of randomness that you expect. Okay. I just want to say a few words about the environment that for-eaches see. The kind of amazing thing about doMC is that so much works automatically because doMC is built on top of fork that you kind of don't have to think about any of this stuff. But it's worth understanding what's really happening, and in particular, when you move to doMPI, you may find that it's more important for you to understand this issue of the environment and what happens. So just a couple of, and I have found that this stuff is not particularly well documented. It's complicated and it's not terribly well documented, so it's worth just touching on. So the first thing is doMC is based on the Linux fork, as I've mentioned before. So the workers that are executing the individual iterations of the for each, they are exact copies of the master environment. So they have everything the master has. They have all the variables and the libraries. And doMC starts a new batch of workers every time it hits a for each. So the idea behind doMC is you hit the for each, it spawns a bunch of workers using fork. They execute on the iterations. When all the iterations are done, the workers are torn down and thrown away, and the master goes on, and if it's another for each, it'll do the whole thing again. So that's how that works. It's very simple, works really well. doMPI is really different as far as this goes. And this is really subtle, but important. In doMPI, Slurm is going to start all the workers in the master. So all 8 processes. If you set up 8 tasks, task 0 is going to be the master. Tasks 1 through 7 are going to be workers, and they all start at the beginning of your R code, and they all are running, doing exactly the same thing all the way till they hit the register MPI. Register doMPI. Sorry, that's a typo. So they're kind of duplicating efforts up to the point where you hit that register doMPI. And at that point, the workers get stuck and enter an invisible worker loop right there. And they're just going to hang around and wait for each tasks to show up. And the master continues on and executes all the following code, including the for eaches and everything else, everything that isn't. So why does this matter? It has a couple of implications. It means that the workers can only see stuff that was defined up to that point, up to the register doMPI. They don't see anything that was defined after that. And they also are going to end up being reused. So if there are multiple for each blocks in your code, those workers will see each of the they'll be used for iterations on multiple for each blocks. Okay, so a little bit subtle. Mostly it works, but if something really strange happens, it's worth knowing that that's actually how it works. And I actually learned all that by talking to Steve. I did not find it written down anywhere. Beyond that, you should be aware that for each is invisibly to you doing its very best to introspect the code block in the for each and figure out all of the things that show up there and to provide them to the workers. So in the case of doMC, there's nothing to do because the fork gives them all of that. But in the case of doMPI, the workers don't necessarily have all that stuff. And so what for each is going to do is package it all up and ship it off to the workers. It does an introspection process on the code block and ships off whatever it thinks is needed. And again, that usually works perfectly, and it almost feels like magic. But you should be aware that there a couple of these other dot parameters, like dot combine, that you can use to customize this. One is called packages. So that tells the for each that a certain package, a certain library is going to be needed, and it should be, the worker should be told to load it, essentially. And you can also force shipping of variables to the workers by doing export or no, dot export or dot no export. So these are ways of fine-tuning the environment that the worker sees. And again, really only matters, as far as I know, in do MPI. It's getting a little bit deep into the weeds here, but I just wanted you to be aware of these potential gotchas, because it can be a little mystifying if something happens there. Okay. That was a complex slide. I want to turn now to a real life example. So a few months ago, one of the researchers that uses our clusters came to me with a code that was running too slowly, and was wondering if there was a way to make it run faster. It was an R code. So this is Annabelle Cardozo, and she was kind enough to volunteer to let me show this code in this course. So this is an excerpt from an absolutely real code that was causing her, to have to wait too long for the results. So this is, as I say, just an excerpt. This code won't run as is, won't even come close. But what's here is real, and it can show you how for each can very easily give you a way to do runs in parallel in R. So what's going on here in this code? I'll try to do this as clearly as possible. There's more code here than I would like for you to have to read. But essentially what we've got here is three nested for loops. So it's triply nested for loops. There's this outer for loop over a set of G's, a middle for loop over a set of L's, and an inner for loop over some repetitions. And what's going on here is she wants to compute a matrix of results over G times L, and for each of those entries, there's a randomization process going on here that wants to be repeated 100 times. And the real work here is being done in this spreadfire function. So triply nested for loops, eventually invoking another function called spreadfire, which is defined elsewhere. And so this, when she came to me, this had been running for well over a week, and it wasn't finished. And that was, troubling. So taking a look at this, I can see, well, we're going to invoke this spreadfire function over 3 million times. Some simple testing showed that spreadfire took about 1/3 of a second each time it was executed. So doing 3 million of those was going to take quite a while. And if I recall right, I think she wanted to run this on even bigger sets of iterations. So at the end of the day, what we're going to get is a matrix of 330 by 100. So basically, G's times L's dimensions, a matrix of that dimension. But the really important thing is, if you stare at this, you realize that each invocation of spreadfire is independent of every other invocation of spreadfire, that they can be done in any order and in parallel. So this is exactly the kind of situation that we love when it comes to for each. So looked like it was pretty promising. Now we could go really crazy and make each of these 3 loops a for each, but it was my opinion that the outer loop had 330 iterations, and that was plenty of parallelism. So to keep it simple and to keep it as efficient as possible, I chose to just parallelize this outer loop. And that's a pretty good rule of thumb that you want to do the least amount of parallelizing that will get you the benefit that you're looking for. There's no point in chopping things up incredibly finely and paying all the overhead for doing so if you're not going to parallelize over more than 330 workers anyway. So here's what the code looks like modified to do for each, and it looks almost exactly the same, right? The major thing that changes here is we're going to replace that 4 with a for each. So that's the first thing we're going to do. The next thing we're going to do is we need to, so here we had a single two-dimensional matrix that we were plugging values into for each of the I, J combinations. So we do an I, do a J, calculate something, and write it into that element of p-burn, a two-dimensional matrix. What I want to do here is, instead of constructing the whole two-dimensional matrix, I want to construct a one-dimensional matrix or vector of just one row of p-burn. I'm going to call that temp p-burn. And that thing is what's going to be returned by each iteration of the for each. And I'm going to use a combiner of rbind here. Oops, didn't mean to do that. To combine those rows all into a single matrix. So you may have to scratch your head a little bit to sort of see how I did that, but it's actually pretty straightforward. I'm just thinking about each iteration of for each is going to produce a row, and then I'm going to combine those together using rbind into the final p-burn. And so I'll end up with my two-dimensional matrix at the end of the day. And other than that, the only thing I really had to do was just the standard boilerplate here at the top of figuring out how many cores I had and doing register do MC. And you can see that here I chose to be a little bit modest and just stick within one machine with do MC. So I was going to get her what she needed in terms of parallelism. But I don't see any reason why this wouldn't work just as well with do MPI. So the result was that with relatively modest changes of the code, it ran nearly perfectly in parallel. It didn't require more memory and required very small changes. So that seemed like a pretty good example of a clear win using for each. Any questions about that sample code? Okay. I'll quickly show you another example of random forest. So random forest is a classification method, statistical method that's pretty well known. And let's see if I get here. So the interesting thing about this is that random forest has a function in its library called combine that knows how to, I should back up a little bit. What random forest does is produces what they call trees, classifications. And random forest is commonly used in cases where you're going to create multiple classifications and then need to merge them together. So they have a combine function that knows how to take multiple random forest results and turn them into a single result. And so we were really fortunate there. We could just use that as our combiner. So we invoke multiple random forests, get a list of them back, and then use the combiner to just combine them into a single random forest. So sometimes you're lucky, and this worked out really well. Any questions about that? If you haven't used random forest, this probably isn't that interesting an example, but if you have, I think you find it interesting. Okay. So I want to finish up with a few alternatives to doing for each. Some thoughts about that. So as I think I've mentioned a couple of times, parallel is a unification of SNO and multicore. So basically anything you can do in SNO or multicore is available, probably with a slightly different function name in parallel. So probably parallel is a good place to start if you're interested in these things. And again, I would point you to Steve's book, Parallel R, at O'Reilly Press, which goes into all three of these. There's a chapter for each of parallel, SNO, and multicore. Again, all three of these things, instead of thinking about things as for loops, they like to think about things as doing a function apply in parallel, and they each have a whole set of slightly different parallel applies that have slightly different operational characteristics, which personally I find just confusing. And then when you combine that with the fact that these three packages, parallel, SNO, and multicore, each have their own parallel applies, it's a lot to try to deal with. But just to give you a sense of what that looks like in it, maybe I'm being too harsh on them. If you get used to this and you like parallel applies, it's just about as easy to use as for each. So here's what that looks like. So here I've got some function f, and I want to apply it to a bunch of values. So I use this function mclapply, which means multicore lapply. So this is very similar to what we were doing with for each. It's basically going to create a vector of values from 1 to n starts. It's going to, in parallel, apply f to each of those values and return the results as a list. And then, we can go ahead ourselves and do this reduction. So this is similar to the combine that we have in for each. This is how you tell mclapply how many workers to start. So you can kind of see that this is very similar to what we were doing in for each, just slightly different syntax. So I can go ahead and believe this will run. So this is basically doing the same thing we did before. So we're squaring the numbers from 1 to 20 and adding them up. And if you look at the documentation of this, you'll see there's just a ton of slightly different functions like mclapply that operate in slightly different ways. That the difference is, do you pre-allocate a bunch of tasks to the workers, or do you let workers take one task at a time, et cetera, et cetera. So it's sort of slightly different semantics on the parallel apply. I mentioned at the beginning the R-MPI library. So what is this all about? MPI is a standard for writing message passing parallel programs. So normally you think of MPI as being something that you write in C or Fortran, but it turns out there are bindings for MPI in lots of languages like Python and R, etc. And so R-MPI is, at one level, it's just a way of accessing MPI from R. And we use R-MPI in the do MPI backend for for each. So it's very useful for that because it knows how to start up processes. It knows how to pass information between different processes that are on different computers, on different compute nodes. But if you directly use R-MPI library, you'll find that it's a very rich package. It's a very complicated package. It can be used in a couple different ways. It can be used as a classic MPI API where you're sending messages back and forth between a bunch of worker processes. But it also has some higher level master worker APIs. I tried my best to find some simple examples of using native RMPI that were both compelling and understandable. And I didn't do really well. It's really a complicated system to use, but this link that I have here is the best one I've been able to find so far. I don't see any reason to use it directly unless you're writing a program that isn't of this characteristic that it's a bunch of independent loop iterations. If what you have is independent loop iterations, then you're much better off either using for each or one of the parallel apply methods like parallel. If you're writing some domain decomposition and you're writing it in R, God help you, probably RMPI is what you're going to need to use. But that's a pretty advanced topic, and I wouldn't use this API unless you really need to. Any questions about that? Okay. So in the last few minutes, the final thing I want to show you is a complete left turn from everything I've shown you so far, but it's useful enough and important enough that I want to make sure that you see it. So if you recall, let me go back up to the top of my presentation here. I said, well, what does parallel R mean? Well, we spent all of our time today on this, essentially. So, an easily decomposable loop because the iterations are independent of one another. And then I just spent a minute talking to you about this. But what I'm going to talk to you about now is this one here. So this is, you've got some R job and you just want to run a whole bunch of copies of it. And the copies are completely independent of one another. They take a different input file, they produce different output file. You just got a ton of them. And if that's the situation that you have, we have a very nice tool called Dead Simple Queue that is not R specific at all. It's basically a tool that'll let you run tens or hundreds or thousands of completely independent jobs on our HPC cluster very easily and with good reporting and good control. And so I just think before you launch into taking if you have this R program and you want to run it on a bunch of input sets, rather than go through the trouble of turning it into a parallel R program, you might think about just continuing to run it as a sequential job, but just running hundreds or thousands of copies of it at the same time. And that's a mechanism that works really well. So the idea behind Dead Simple Queue, the fundamental idea is that you create a job file that contains a bunch of jobs, one per line, and those jobs can be anything. In this case, there are executions. So one job consists of first loading the R module and then running this R script on some input parameters. And you can imagine that this file could have tens, hundreds, thousands of lines in it. So that's your input file. And then you just go through this process of setting up Dead Simple Queue by loading the module, and then this utility here, DSQ, creates a batch script. And you give this utility the name of the file in which you put all your commands, and it will then be referred to in the batch script. And then you just run the batch script and everything will work beautifully. It'll run each one of these commands in a separate task and produce a separate output file, and all works great. And what we usually do, these job scripts are fine to write by hand if they're small, but once they get larger, you know, if it's hundreds, thousands of lines, you'll usually want to generate this job script with some helper script. So I'll usually write some sort of helper script that auto-generates this thing. So let me show you that for real here. Again, we have this as an example. Let me see. So here's an example job script that has 40 lines in it. And you can see I'm basically running just the same R script with different input parameters. Okay? So that's the first step. And I auto-generated that by this script. So this is a very simple R script that generates that file, makejobs.r. And now to actually go ahead and run this thing, I do module load dsq, and then I could say dsq job file equals jobs.text. And now I can put any other Slurm parameters that I want. I could say -p, scavenge, and let's say I knew that my job needed a lot of memory, each of my subjobs, so I could say 10 gigabytes. And so it generated for me this job script. If I look at that, most of this looks like a very familiar job script. We can see here is where my actual list of jobs got stuck in. And the rest of this up here is just pretty much standard Slurm stuff. You don't normally have to look at this file at all. Just go ahead and sbatch it. And you can see that it's submitted here as a job array of 40 different subjobs. And I'm not sure how long it'll take for this to get going. I submitted on Scavenge, so it doesn't have high priority. Oh, there it goes. So now it's been expanded into all 40 jobs. So at the moment, all 40 of my jobs are running at the same time. They're scattered across lots of different compute nodes. And they kind of can fit into wherever there are free CPUs across the cluster. So that's basically how that works. And when it's all done, it will produce an output file. As each subjob is computed, an entry is made in this status file that has information about the job. It basically says the ID of the job, the success exit code of the job, where it ran, when it started, when it ended, how long it took, and what the actual job was. So we have found people running lots of independent calculations. This is a very effective tool and very easy to understand. So I wanted to throw that into the mix here of running R in parallel because I think it can be really helpful in certain cases. So just to contrast Dead Simple Q against For Each, one really nice thing about Dead Simple Q is it's more adaptive. If you think about the For Each, or any of these standard parallel R methods, you say how many resources you want up front. You want this many nodes, you want this many CPUs, you want this many CPUs on this many nodes. You're going to get nothing done until the system can give you exactly what you asked for. You need to get the whole, if you say I want 1,000 cores in order to run this parallel job faster, the system is going to keep your job waiting until 1,000 cores are available all at the same time. In contrast, Dead Simple Q will submit 1,000 tasks to the system, and as CPUs become available, they'll just start running. So maybe at the beginning you only have a few tasks running because there's only a few cores free, but then more and more will begin to run. And so you can your usage of the resources can grow and shrink. You're not saying I have to have all of this at once. On the other hand, the nice thing about for each, especially for each using doMC, is that most of the memory gets shared between all the different workers because of the way that fork works. In Dead Simple Queue, every task is a completely independent process. It's not a child of the master process. And so each Dead Simple Queue task ends up needing its own memory. And if your data set is very large, that could really add up. So a very large model run on for each on a single node, all those workers will be sharing the memory, whereas with Dead Simple Queue they won't. Each Dead Simple Queue task is a separate Slurm task, so there's a few seconds of overhead per task. So your tasks had better be coarse-grained enough that makes sense if you're going to use Dead Simple Queue. Whereas for each, it's a fork. Forks are really fast. At least for each with doMC. The greatest thing, of course, about the Dead Simple Queue is you don't have to change your sequential program at all. It's exactly your sequential program that you're running. On the other hand, you're going to have to manually worry about how to combine all the results into one final result. You usually end up having to write yet another script to combine the results. So for each, that can be a little bit complicated. So pros and cons in each direction. I'm going to finish up here with just a few final resources for you to look at. The for each vignette. If you poke around in these vignettes, you'll find all kinds of interesting things. And like I said, the documentation for a lot of this parallel R stuff can be confusing and complicated. Often the best documentation you can find is these vignettes that are stashed down under CRAN. And I'll just also remind you to be cautious as you Google and find people's examples, that you try to be clear in your own mind when you see an example, which mechanism are they using? Are they using for each? Are they using parallel? Are they using snow? Are they using multicore? And because otherwise you'll find yourself getting really confused. Or even if they're using MPI, RMPI. So that's all I have for you today. I thank you for your attention, and if you have any final questions, I would be very happy to try to answer them. So thank you.
We have a question.
Okay.
What if you combine for each with DSQ? What are the expectations or guidelines regarding how many cores and machines we can or should request?
Sure. I have never done that. It should work. So it's certainly possible to run parallel jobs as individual tasks within Dead Simple Queue, within DSQ. However, to some degree that goes against some of the advantages of Dead Simple Queue, because you're going to have to run fat tasks, tasks that are asking for lots of resources, lots of CPUs, in order for that to make sense. And that's going to limit that's going to limit Dead Simple Queue's ability to sort of find a few available CPUs here and there. So that's one downside. In terms of what you can ask for, that's a little tricky to answer, because it really depends on the cluster, it depends on the time of day, it depends on the partition that you're submitting to. I usually find it's pretty easy to get 20, 30, 40 CPUs, regardless of which mechanism you're making use of them with. If you're asking for hundreds of CPUs, especially if you're asking for, I think what gets trickiest is if you're asking for whole nodes. So if you want all the memory on a node or all the CPUs on a node, And the system has to find, completely idle compute nodes for you, and that's when it gets tricky. So I think you have to experiment a bit and see what works on your particular cluster on the particular day you're working. But I think if I were to combine the two, I would go kind of modestly. I would have lots of dead simple queue tasks, but the individual dead simple queue tasks probably shouldn't ask for whole nodes. They should ask probably for a handful of CPUs and not a ton of CPUs, because otherwise you're just going to spend a lot of time waiting.
All right, we have another question, not directly related to parallel computing. Could you briefly show how to create run an R Jupyter notebook on Open on Demand?
Sure, that's an excellent question. So the first thing you need to do, Leah, let me show you. That's probably the best way to do that. So for those of you who are, I apologize, I should have explained this better than I did. So Open on Demand is a relatively new, a new tool that we have on the clusters. It's basically a web-based access to the clusters, and it can be used a lot of different ways. It's an open source project. It's really nice. I encourage you all to try it out if you haven't tried it. So just to kind of get started, you go to OOD-cluster name, which right now, we actually now have it on RUDL as well. So it's on Grace and Farnham and RUDL. So you go to this URL, and it'll CAS log you in. I'm already logged in, so skip that, but normally I would have to log in with my CAS. And from here, you can do lots of different things. So if I do shell, this basically just gives me a login on the login node. So this is just like if I SSH'd. So it's useful, but maybe not that earth-shattering. But more interestingly are these interactive apps. So we're slowly adding more and more things here. RStudio is probably of interest to you guys. So this will basically start in RStudio. I can show you that. So it gives you this panel, and you go through and fill in all these options here, most of which are fine, and then launch it. We'll do that, and then I'll come back. So what it's doing right now is it's waiting to find an allocation, and it's going to launch RStudio for me. But when actually it did. Okay, so I come in here, and here I am. I'm in an RStudio. I'm on a compute node. I can do serious computing here because I'm on a compute node. I have as many CPUs as I asked for, et cetera, et cetera. So that's RStudio. But the question specifically was, sorry, let me get back to where I was. So I'm going to go ahead and delete that. Was Jupyter Notebook. So that works similarly. You can specify different things about the job you want, how many hours, how many CPUs, all that stuff. But the critical thing is here. So normally what you would see here is this one. So this is the environment that the Jupyter Notebook is going to see when it starts up. And by default, we provide you this one. And this will not have the parallel R stuff in it. Okay? So what I did was, outside of all this, in the normal way that I showed you in the presentation, I created a Conda environment that had everything I needed in it. Okay, so that was here. So I did this stuff. Okay, and that created in my environment a new Conda environment called Parallel R. And when I did that, or having done that, it's going to show up in this pull down. And so I just select it, and that's good. And then I'm good to go. And that's exactly what I did before you all joined the presentation is I basically did launch. So that's what this one was. That's the one I've been using. We'll just see if it starts up quickly here. So it's waiting to get, okay, it's starting. So admittedly, this is a combination of a couple of complicated environments, and can kind of got to wrap your brain around it a little bit. But it's combining a rich Conda environment that I created myself, and this open on demand, which knows how to start Jupyter. So this brings me into the Jupyter notebook, and from here I can navigate down to my repo, start up the notebook file, and with any luck, yeah, so you can see I'm running the R kernel here. That's what that means, and this is exactly what I was showing you. So this is a live environment. Is that good enough?
Rob, we have 2 more questions about Open on Demand.
Sure.
Are there plans for it to become available on Milgram?
Yes, there are plans. We're working with the security folks at ITS to get permission to do it. It's as you can imagine, every time we have a new way of accessing Milgram, we have to go through a security design review, and so that's kind of where we are. But we're hopeful that we'll be able to do that. We recently just did it with Ruddle. If you use Ruddle, the only trick with Ruddle is we have the force duo authentication to get into Open on Demand, and that took a little bit of doing, but that's available now. Any more questions?